So if you are interested, you can get to look English or just taking some related knowledge with this online. But I think just for this boundary conductor or this remaining part, okay, so you do not need to know how this formula comes from, but knowing that when to use it. Okay, so if you need to use this formula, directly, you do not need to
No, how this
difference everything. Okay.
That can you please just open this PPT? I need to do it.
Okay, so we need to start recording, but this is clear to you, of your domain is and nor coming here yet, so we will start at 25.
Okay, but I just want to make this focus. Because this focus
is okay for this page. Yeah, the nature 5, and we will not discuss with more details of this lecture, but I'll give a quick view of this remaining part. Okay. So, how do you feel about how you feel the difficulties of this homework? Is it easy or difficult? Or you think you believe this will be too many actions for one homework? Or you prefer the smaller amount of the actions in one homework? I beg your pardon, please?
Yeah, little bit difficult.
Difficult? Okay. Okay, so could you present you the low-level actions in one homework? Okay. Oh, no. You do not need to just do research or just to remember this, because we will just to go through this the remaining part. Okay, so this is a very maybe a little bit difficult part of this to solve the inductions, but so you only need to know when to use these formulas. You do not need to know how it is done. Okay? Great impulse in your result here. Just like this, this. Okay. So you only need to know the rulings and the error. Okay. So another the last one. So next let's start with the remaining part of this lecture, okay? And previous lecture we were just to learn how to calculate the line darkness, okay? So for the single line and the bounding, okay, so we have not discussed the bounding. So we have just to start with this part, okay? So okay, just knowing that this formula is like this, you don't need to know how this formula is come from, okay? And so this is the 9 examples. So, and for these situations, so it will be our real applications of the transmission line. It actually will be 3 or 4, yeah, each for one transmission lines, and we will see the bonding with that bonding together to be the real transmission network of our real work. Okay, that is similar to this. So in the real world, actually, so we discuss our problems. So we will always just assume that our network or the system is in a balanced system, right? But in the real world, so it's actually we see that the distance between the phase A, B, and C is commonly not equal, right? So they are not share the same value. So that it's actually very difficult to get a balanced three-phase system in the real world. So that's why in these transpositions, okay. So because we need to push the unbalanced three-phase system in our real world to be the balanced, okay? So we use this method of rotation, okay? Let's do like this. So phase A, phase B, and phase 3, phase A here, phase A here, and for these, we will call it unit, 9 unit lines of this transmission network, okay? So we'll say each phase of the phase ABC will be the second position, the first position, the third position, okay? So in that case, the three-phase system in within one unit length is like this. We will have to view it as a balanced three-phase system, okay? Although it's actually the three-phase system ABC here, it is not it's the unbalanced system. But by rotation, it will become the balanced system. Okay? Like this, you can see, yeah. This line will be the voltage. It may be a little bit ambiguous, but you will see it like this. Okay? Okay, so we'll get started another lecture. So we have maybe 1 or 2 more lectures about these transmission lines, and then we're just going to the system matrix and the power flow, okay? So it will be maybe okay, so we will get a quick review of our electric fields. So in this lecture, we are not doing our research, we're not focusing on the magnetic field, okay? So magnetic field is our previous, we discussed in our previous lectures, and this is the electric field, but it's quite similar to the magnetic field, okay? So the Gauss norm over here. So QE, so do you know this? QE to electric charge. Okay, so you know that electric charge, and so this is the electric flux density. So it's practically assembled similar to the H. So the magnetic field density, okay, the magnetic field is equal to the D. So in the previous lecture, okay, but they are in the magnetic fields, but today we're discussing about the electric field. Okay, so integration of the D is equal to the electric charge here, okay. So A is the area enclosed piece, okay, enclosed the surface of this electric field, okay. Okay, so there is one examples here. So this is the transmission line, and this is the surface which the electric fields were just to going out. Okay, so you can understand that the temperature is the transmission line in every field, but in the 360 degrees, or directions, but or perpendicular is the transmission lines. Okay. Okay, so here's the example. So we need to calculate the D. Okay, so electric flux densities is here. Okay. So what's the density of this electric field really is? About this system, okay, so we're also assuming that this transmission line is infinite enough, okay? And we're just to that has a charge density of the tube, okay? The tube coulombs is a unit of the charge, okay? So this, coulombs represents the electric charge, okay? So the density is coulombs per square meters. Okay, so because the D is the radially out, match this. From this transmission line and from the transmission line to the outside world, okay? So we can get to the integration of the cylinders under the wire. This is the cylinder, right? We assume that is the surface in the cylinder enclose the transmission line. Okay, so this is actually is the surface A, right? The enclosed surface, the cylinder here. And so we are also the perpendicular to the end of the cylinder is actually so perpendicular or vertical with this transmission line. Okay. So in that case, the integration of this electric field, electric flux density, okay, density is quite easy, right? The D occurred with the area of the cylinders, right? Because the noise is the edge, and so this noise of this circle is the 2 pi and the radar, okay, radius. So and the integration of this flux density is equal to the electric charge. The electric charge then is equal to the Q according to H, because Q is the density, okay, the coulombs per meter. So the H is the mass we assume, okay, assume the cylinder. So that we can get these equations, okay. So the D, the large electric flux density, can be described by this, and so the A R here represents the vectors, to describe the directions of this, because this is the vector, because you can see this is the bond, this is the both sides of the both bond, okay, both bond here, so it's a vector, so this just to describe the directions. Okay, so it's quite similar with the magnetic field. Okay, so E electric or density refer to the small part with E. Okay, so have you remembered this in our previous lecture? So in the magnetic field, okay, so the permittivity of the free space 0 and the relative permittivity, okay, it's also the same value 1, approximate 1 for the L and 2 or 6 for the most geometrics constant, okay, geometrics is like the plastic or just like the spoon or just like the not the water, not the metal, okay? Okay, so this is the geometric constant, okay? So the wood is the geometric, okay? However, yeah, it's actually with higher capability to defend the flow or the cover with the electricity, okay? So we call it the geometric constant, okay? Electric fields and the permittivity in the electric field, okay? Okay, so in light of the electric fields, we can calculate the voltage differences, okay? Actually, voltage is the differences value, okay? From one point to another point. Let's see, if there is a one system or network and one of these ends is grounded. So we will say that the grounded is a huge sphere of the Earth, okay? So we will say that the voltage of the Earth is 0. So that it's why we call the source, the voltage source, from the voltage source to the ground is the voltage that the source can produce, okay? So because it is the voltage minus 0. But here, in n2 points, okay, we will just assume that the R4 and the theta, okay? So in the 2 points, so and we can use the integration to define the voltage differences between these 2 points, okay? So it's actually the integration of the electric flux densities from this point alpha to the theta, okay? Why there's minus? Why not why there is the minus, not the positive, why negative?
Because we find B beta A, but our integration is P of alpha minus beta. So this is negative.
Yes. You can just to explain this by this is the mathematic view or the mathematic angle, but for the physical point, okay. So the minus means that the voltage is actually to get some to consume some energies just to push back from the point in the lower electric field to the higher point, okay? So we have to assume some energy just to push this one point to the higher point, okay? So the point in the lower position to the higher positions, okay? So we're right with negative.
Because our voltage is rising.
Yes, it's actually okay. So the previous examples, okay. So let's say you remember this. I wanted to use this So we would have to here assume that these 2 points in the previous systems here, okay, there will be 2 points, the same system, and there will be co-terminals with as well, okay. So we will just assume that the R to be the radial distance from the well to between the points alpha and beta, okay. So the distance is R, okay, uppercase R, so that if you get this, you can see the L, the differentiation of the L and differentiation of the R. So what is the volume? So what is the L?
This is the length, derivative of length,
Yes.
and this is derivative of radius.
Yeah, you're right. It's actually so it's small, very smaller L, but we will view it as a unit. Okay, so this is a very quite small unit L. Okay, so because the electricities were doing this, and so here is the directions along the transmission line, but here is the directions perpendicular with the transmission line, okay? Okay, so the voltage difference between these 2 points, okay? So here we also assume that there is no relative permittivities, so that we'll assume that the relative permittivity is equal to 1 because we're assuming the L, okay? L is equal to 1. So we just to calculate this. So the voltage between the beta and the alpha, okay, equal to this. Because in this integrations, the differential voltage is uppercase R, the radial distance, so that this four are the constant with the charge, okay, charge. And so this is the integration of the y divided by the uppercase R. You know how to calculate this, okay? Here. Yeah, you remember the calculation method? Okay? Okay? Okay. So we're at these final expressions, these voltage differences between any 2 points. You know this. Okay. So this is also the same expressions. Over here you can just see that so Q, the electric charge is positive. If the Q is positive, so these points closer to the charge have higher voltage. Okay, so this is a positive voltage source. So the point that is closer to the voltage source, of course, will have the higher voltages. So why these fractions in the previous page can say this, why the negative here, and here's fresh explanations for the voltage between the 2 points is equal to the energy required to move 1 coulomb charge against the electric field between 2 points, okay, to push this electric charge from the lower voltage point to the higher voltage point, we will consume the energy. So that's why the negative. And third one is voltage is infinite, which is one of the points to be the infinite far away. Infinite far away is actually you can just choose voltage on the grounded. Okay. So here is a multi-conductor case. In the previous case, there will be just one transmission line, and we assume that we have n parallel conductors. Okay, so the n transmission lines together. So at each transmission line will have the charge densities of the two I. The I is the ith conductor, is the ith the transmission line. Okay, so that the voltage difference between the 2 points can be defined like this. Okay, you can see, this is the voltage differences in one conductor or one transmission lines. And for this, because there is n conductors, it actually we need to simply sum to add all of them are, okay, sum up of this value. Because the electric charge in different conductors is not different, so we have to add them up, and also these two parts is also the same with the previous, with a single conductor situation. Okay. So the R for I and the beta I is equal to the radial distance from the points alpha and the points beta to the ith conductor. Okay. So it will be a little bit different with the previous case because there is only one conductor and we have the n conductor. But in this equation, we're just focusing where we are focused on only one, on the conductor I. Okay, so doing like this. And so we are firstly assume that the sum of the electric charge is equal to 0 because this system is not a generator nor the node. Okay, so it is a complex. It's a complete system. Okay, it's a whole system, so that the system will not send out the power nor receiving power. In that case, so the sum of the electric charge will be 0. Okay, because we are not discussing about the generator or nor the nodes or consumers. Okay, so the sum of the electric charge will equal to 0, and we're just to divide this to the two parts. Okay. A, the line A, do these two parts. The R for I is here, and you can understand this. Okay, the line multiplication line A and B, line and A multiplied with B is equal to line A to the line B. Okay, so this. And we were just to use these as variables. Why these variables is variable? Do you know? Why this is equal to 0, while these two is not equal to 0. So you can see here. So we assume that is 2 is equal to 0. Okay, so this is our assumptions. So do you think this one is equal to 0 or not? It might be 0, but if we are not always equal to 0, okay, so you understand that minus 1 is the positive 1, minus 1 is the positive 1, but here is the 2, here is the 1 divided by 2 is not equal to 0, okay? So that although the sum of the electric charge is equal to 0, but these two will not equal to 0. Okay? So because Q1 multiplied by one value and Q2 minus another value, these two, this value, the 1 divided by the uppercase R, the distance here is not the same. Okay? But y for this is equal to 0, so
because there are one function, sir.
yes, it's actually, you can say, because here is the distance from the R4 to the Y, so you can say it as a constant value. It's only one variable. You can just to place this constant value here, okay? Because this is the sum of the I, okay? So I from 1 to the N, but it's nothing to do with this, because it's only the distance from the R4 to the first conductor. So this is the constant value. You understand? Okay, it's the value here, and constant value, and this one is equal to 0. Okay, 0 multiplied, constant value multiplied with 0 equal to 0. Okay, so this is the 0. So the first part minus 0, the second part minus 0 is okay. It is still equal to the voltage differences. Okay. So we can just to break down like this. Oh no, we were just to use the second part to minus the 0, because we can see the first part is still the same, but the second part, let's say the line or the R part, the distance between the R part to I is divided by the R part to the first conductor. Okay, here, okay, you understand? Okay, so the next step, we assume that the R bar or target conductor or the target point in the infinity is very, very far away. So this line is approximately 0. And why? So why this one is equal to 0? So anybody have any point with this? So R is very far away.
Like infinity.
Yeah, exactly. Very, very far away. So very non-distance.
1 by alpha equals 0, sir. 1 by infinity equals 0. Sir, if alpha is very far away, so 1 by infinity equals 0.
No, that's the line. No. Oh, the infinity one. Yeah, you're right. Okay, you're right. And actually, you can just to believe that this is alpha. This is the conductor I. Okay, this is conductor 1, and this is alpha. It's very, very infinite because it's very far away. and this is the distance from the RI line, okay? So if the R is infinity, so what is the R distance between the conductor I and 1 will be 0, okay? So 0, okay? Because it's very, very far away, so this is a negligible distance, okay? So that 9 so because this 2 is distance between these two is 0, so it's actually the 1 point, okay? This 1 is equal to 1 point, and so this is the stand, will be the stand distance, okay? So that it means the alpha from alpha to I and from alpha to 1 is equal to 1. Equal to what? 0, okay? 9. You know the mathematical expressions, 9, okay? Oh, here's 1.
Yes.
That's 0. Okay?
Yes, sir.
Okay, so you can understand all this page, everything in this page. Any questions? So, and actually, you do not need to just to recite or to remember every steps. You just to know that, because I believe this formulation, the process formulation is not useful. However, these expressions or just like these solutions in the mathematics, you can use this in mathematics. I think this is the most important part of this page. Okay. Okay, so here we will define the absolute voltage. Okay, so you can see because this one is equal to 0, so this one is 0. Okay. So we can just to define the voltage of the point. So with respect to the reference voltage and the infinity or the ground is both okay. Okay. So this is absolute voltage. So it's actually, if you are learning the class, if you are in the class of the circuit theory, you can see that each point, the voltage in each point, and you can see the voltage in the point 1 is 5 volt, the point 2 is 3 volt, and the professors there were very low. It's actually describe the voltages is our absolute voltages.
VAB, like these 2 points, 5 volt,
Yeah.
3 volt,
Yeah.
VA, VB, so VAB equal, this is VB, about this distance is
Yeah, exactly. Okay. So here you we correlated the absolute voltage of the 1 point. Okay. In this. Okay, so for measuring this point is within the well or outside the well, it will be the same expressions. Okay. Okay. Next page. Here is our 3 conductor phase rack, and we also assume that it is a symmetry, so it will be the balance system. Okay. So the A, B, and C each will be the same distance, okay? The same distance from other two, the uppercase D, uppercase D, okay? So we will also assume that this is the whole system, so there will be no more electric charge going out or coming, okay? So the sum it will be 0. And so it's equal to use our previous, okay, with this equation, with these formulas. V, A, so absolute voltage of the point phase A here is equal to this, okay? R is the radius from the phase A. So this is the point to calculate the point. What is the difference between the point A and the phase A, okay? And so here's the thing. So do you know how to calculate this to this? So do you know this? But remember that the sum of the A, B, C is equal to 0. Okay, so here is the expressions here. 1, A, B, C, 3. And we can get QA1. The QA multiplied with 9, the uppercase B, the 1 divided by B, okay? We add 1 and then we minus 1, the same variables, okay? So we put them together. This is okay. 1 divided by the uppercase B, this equal to this, okay? This is the variable. This is the variable, okay? This down. This 2 is equal to QA 9. Okay. So I think this is also very important. The idea of the solutions in the mathematics field. Okay. So we can get to add 1 variables and minus 1 variables. Is sometimes will be quite useful. Okay. So and for the non-competitive compactness, so the electric charge is equal to the C multiplied with voltage, okay? So this is expressions by the capacitance to the electric charge. So as to wonder, have you guys just learned how to calculate this matrix?
Yes, sir.
You have learned about this?
Yeah, the homogeneous matrix.
Okay. So that in the situation of the multiple conductors, because just like that there will be many transmission lines, okay, in these situations, we can use these equations, okay, because Q is equal to C factored by V, okay, so it's the matrix C, matrix V, and here is the capacitance within the conductor N, and so this is the mutual compactance from the line between the conductor 1 and the conductor N, okay? So here is the matrix expressions. Okay, so considering the mutual capacitance, okay, so we would like to eliminate the mutual compactance we will assume a uniform transpose line. Okay, so remember at the beginning of our lecture, this A, this A, this A. Okay, so in that case, we will still have the balanced three-phase system, so transpose line. Okay, so it's actually the similar steps of the eclipse of the inductance in our previous lectures. Okay, so we have to get the expressions with this. Okay, very similar and inductance. Okay. And also, we remind of these conclusions of the keys of the 9 inductance. So for the n bounded conductors, okay, so we will have to go through very quickly in the beginning of the lecture. Okay, we're testing this one. And for this part, the capacitance, the inductance, you need to know how to. You just need to know to use these equations to calculate. Okay. Just like I will present you the calculation, these formulas, and I will give you the parameters. You know how to calculate this. Okay, so we're just going through more quickly. So we can just do just to based on the expressions of the single line phase situations. Okay, so this is the one phase or one transmission line situations. This is the bounded. There will be 3 or 4 transmission lines come together. And for the GMD, stands for the geometric mean distance. And it's actually I will show. Yeah, here is two commonly used the expressions of the radius. Okay, so the GMR, the GMD. So we want the geometric mean radius and geometric mean distance from this A to this B, and the very quite commonly used to in the bounded transmission line. Okay, so there is the two expressions. You know there is a GMD and there is a GMR. Okay, so if you use age, you search age. You can just do with age in your textbook. You can search it online and get these expressions. Okay. In that case, we're going to extend the one phase expressions of the capacitance to this here. Okay. And here is for the bounded for the multiple transmission line situations. And here is the example. Okay, so we were not to calculate these examples, but I'll show you this quite easy that. So this is the GMR that use these equations, and the DM uses equations. So use the GMR and GMD equations is present to you as capacitance with these all these values. So the reductance, okay? So reductance of the capacitance, reductance into, you know this, right? Is omega, for the C divided by 1 divided by this 2, you get this. So it is actively impeding impedance of the compactance C, okay? Compactance C. So the formulas they provided, you know how to calculate this, okay? Any questions? if I were present you all the formulas, to make.
Yeah. But I know one formula XC, like relaxation equal minus 1
Yeah.
over Z.
But
What is it?
and the J is sphere, okay? So in this part, in this page, that we were to consider the magnitude. We were not consider the angular, okay? So you can also cross this J, and here is 90 degrees.
Okay.
So
What about the 2 pi into exponential?
for what? 2 pi?
2 pi into ER, is that one?
This is the
Square.
epsilon value, 8.85 into 10.
Yeah,
So,
here,
this level.
yeah. And we it also assume that in Israel, so the relative permittivity is equal to 1. Okay. So these parameters, there is questions in the homework or examinations I will present you. Okay. You do not need to research. As I said, we are not the plots of recession. Okay. So this is actually the transmission lines of the real world. Okay. So here is the sphere strand core, right? The sphere core in the conductor. Here is the luminous strands outside. So it's actually here is the one transmission line here. Okay. So we call it the SSR, the aluminum conductor sphere reinforced. Okay. That's doing same as this. Okay, so this is our real use to be applied in our real world. Okay. Okay, so also conductor area. So okay, so we will not need to know this. Second one, know this. Equations. So have you do you remember what is the effective radius?
Victic radius.
Yeah, you know this R equal to this. We will calculate this in our previous lectures when you calculate the inductance. Okay, so this is called effective radius, and it's okay.
0.78 R.
I'll make a double check. It should be in my memory. It should be yeah, that's it here. Yeah, it's very fatty videos. Okay, so the final part, the inductance, the capacitance of the transmission line. So we have completed this two, and so the easiest one, okay, like the distance. Okay, so easy, right? The resistivity divided by the area, the area of this transmission, the transmission lines, okay. So you can say that the resistivity of the aluminum and the copper is different. It's actually the
I know R equal rho L by A. Now where is it?
rho. Yeah. In your formula, so the rho is the unit value. Okay. So this is
L. Where is L, sir? I know R equal rho L by A.
I say per unit.
Line
This is the per unit. Okay.
This is the line resistance.
Yeah, if you need to get the total resistance, you can get the what total resistance. Okay. So you can see that the copper is the north and the loom, okay, loom. So the resistivity is the north, the better, okay. So there will be the much more north in our transmission network. So it's actually the silver, the gold, the silver, the copper, right? The silver has a much lower resistivity. So, but do you know why? We not, it's actually in China, we will not use the silver to use copper. Yeah, why do not use the silver?
Because this is the high resistivity. This R equal rho by A. If you
But the silver has a much lower resistivity than the copper. So why not use where we do not use the silver?
This is not good. This is not better than copper, like as a conductor. It's expensive, look.
Yes, actually, it's the best thing. Okay, so for one thing, for the utility, we're just spend much more money to build the customer network. For another thing, you may find that we need some seed, with much more seed to get effect on your transmission line, because the silver is one of the valuable metals, okay? So although it's maybe cheaper than the gold, but it's much more expensive than the steel. So that the most part of the work in our country uses copper, okay? So this is one example. So you can see the resistance, very easy to calculate, okay? And the area, this is the area of the circle, the square of the radius, okay? And you can see it is the O per mile. So the Y is no, the noneness of the. Okay, so AC current, so it's actually we use the AC current in our network, in our transmission network, okay? So to flow towards the surface of the conductor, the resistance is like higher than the DC. So it's actually, so the DC transmission networks and actually has some advantages compared with the AC current, okay? And the second one is the resistivity, and this non-resistivity will be also increased when the non-conductor temperatures will increase. So that, and we discussed about the transmission limitation, that the limitation of the transformer power is limited, okay? So there is a limitation after limitations. We cannot to send much more power in one transmission line, because more powers means the higher temperatures, also means the higher resistitivities. Then finally the much more losses in the transmission network, okay? Okay, so then given these, okay, so if you would like to become an engineer in the utilities, maybe sometime, and if you are in the maintenance team, the team that to maintain of the transmission network, the transmission lines, the substations, the transformers, you need to find some useful data, parameters in this table, okay? So this is inductance, the impedance of the inductance, okay? So impedance of the inductance and the impedance of this capacitance, okay? So we can have to use this table to get all required parameters to get this total impedance of one transmission line. Okay, some transmission topics will not cover much. Okay, so the multi, the fluid lines, the papers, papers in our country will be the one. The major part of the papers will be overhead, okay? So in the open air, you can see, and some part and very small part of these papers will be underground. Some of the papers, okay? The ground as well, so this hyper transmission network will be also you use your socket, okay, will be the three lines, one, two, one and two, one is for the four with the 5 lines and another one is for the 0 lines. And the third one is actually the grounding, okay? That's like your three-pin socket, okay? So one is for the grounding because for the large power electricity applicants, so it will be more safe to use this grounding lines. The rubber discharge, okay, shunt, conductance, and DC transmission lines, okay. Okay, so we'll have the bridge, okay. We'll have the bridge before we start the lecture 6. Six is the lecture 8. What's that?
Why?
Something is really difficult. And I can show you, but as in S7, we will be require some very difficult solutions, as like this. Machines, complex. Okay, so for some list functions, so okay, so we will do not cover this, and if you are interested, you can just read the textbook. So there will be much more details than my PPT I use. Okay, so that's how to bridge. Okay.